Okay, so here we see a interference pattern with the bright fringes of double slit inside the center bright spot of single slit. Our first job when seeing this intensity pattern is to figure out the ratio between the spacing of the double slit and the width of the single slit. The reason we can do that is because the spacing of the double slit, let's say we have some perfect double slit, and here is the center with a bright spot. Then the spacing between the bright spot will be the y position, the height of the location of the first bright spot to the center, and that will be theta 1, which is the angle for bright fringe of the double slit, which follows from this formula. Start with n, and then you can replace n with 1 for the first bright fringe above the center. So this is the angle, but if you want the height of the first bright fringe, we should multiply the distance here into tangent, and that should give us the y1 we want. The thing is that when the angle is small, tangent and sine is the same, so we can use the formula of sine to replace tangent, and that gives us L lambda over D. So we know that the spacing of bright fringe should be L lambda over D, with L the distance between the screen and the double slit. Now, we can do a similar thing for single slit. In that case, the size of the center bright spot will correspond to the angle of the first dark fringe, which the angle follows this formula, with the A as the gap, the width of a single slit. So if I want the entire width W, then I can look at half of it, which will be, again, L times tangent approximately equals L times sine, which is just 1 times lambda over A. So that will be L times lambda over A. But that is just half of W. If I want the entire W, I should multiply it by 2. So I know the whole thing should also equals twice L times lambda over A. So by looking at the ratio between the width of the center bright spot and the spacing between the bright fringes, we can get the ratio between A and D, since the distance to the screen is the same and the wavelength of the laser is the same. Now, we see that this center bright spot is as wide as 1, 2, 3, 4, 5, 6, 7, 8. This is the spacing between dark fringe, but because the spacing between dark fringe and bright fringe is the same for double slit interference, so I can just count the spacing between dark fringe, and I can count 8 of them, so I know 8 times the spacing between the double slit bright fringe equals the width of the center bright spot, and that gives me the ratio between A and D, which is 8 times A, since all the lambda and L cancels. This is 2 times D. So A for A equals D. So with the ratio, we also know the sum of A and D is given in the problem statement, which is 250 micrometer. So if the sum is 250 and the ratio is 4, I can replace this d with 4a, and then I get 5a equals 250, and then the width of the single slit is 50 micrometer. And I also know the center bright spot is 4.8, which equals L, 2 meter, lambda, something that I can solve now because now I have A. So I can move the thing around. Lambda should be this thing, let's call it W. W times A over 2L. So plug in a number, 4.8 centimeter. A is 50 micrometer. L is 2 meter. So 2 times 2 is 4. That cancels the 4 as 1.2. And that times 50 will be 60. Then this is 10 to the minus 2, 10 to the minus 6, 10 to the minus 8 meter. So that will be 600 nanometer. So now I know the wavelength. This is the wavelength of the laser. Now, after I know the laser's wavelength, I can figure out the refractive index of the glass. Here we see that at the center, we have a dark fringe of the double slit. That is weird. Usually the center should be bright fringe. This is because the glass down here caused a phase shift such that the two waves have extraordinary interference at the center. This means that a two wave should leave the slit with a phase shift either pi, 3 pi, or odd number of pi. Now we know that if the refractive index of the glass is bigger, it will generate more phase shift. So the smallest refractive index corresponds to the smallest wave shift, smallest phase shift that corresponds to disruptive interference at the center. So we know if we want to solve for the smallest refractive index, we want to solve for the refractive index that causes a pi phase shift between the two waves. So on the top of the fringe, double slit, the wave passes through nothing, and for the bottom, it passes through glass. So the wavelength here will be lambda, but the wavelength of the wave inside the glass will be shorter. We call it lambda prime. So let's say the phase of the wave on the top is 0. Same with the bottom one, and they should start with the same phase as the laser coming in to the double slit is a single laser. After passing through a thickness tau, the phase of the wave should now become k times the distance it traveled, tau. So that will be 2 pi tau over the wavelength. The wave of the phase of the bottom wave after traveling through the glass will accumulate again k times the distance traveled, but here k will be different because the wavelength is shorter. So we know it will be 2 pi tau over a shorter wavelength, and we know it will be n times shorter due to the effect of refractive index. So if the two phase end up having a pi phase difference, then 2 pi tau times 1 over lambda prime minus 1 over lambda should be pi. So lambda prime is different by a factor of n with lambda, so you will get an n minus 1 at the end. Here's a lambda at the denominator. So you get n minus 1 should be the pi cancels, lambda over 2 tau. Lambda is 600 nanometer, tau is 1 micrometer, so it will be 0.6 over 2 equals 0.3. So at the end, you can add that back to the n over here and get n should be 1.3. That's it.